Hello, everyone. My name is Ioana Zelko, and I'm a postdoctoral fellow at the Canadian Institute for Theoretical Astrophysics. Today, I wanted to talk to you about the cosmic microwave background absorption by dust. Due to the speed of light being finite, we are able to observe earliest moments in time by looking at larger and larger distances away from us. In particular, we are trying to detect the radiation coming from the beginning of the universe because we're hoping to see if we can prove that theories of the beginning of the universe, such as inflation, are correct by seeing their imprints on this earliest radiation. However, there is a challenge to these measurements that comes from the fact that we have to detect the radiation coming from here after it has passed through all of the components of the universe, because we are here normally observing either in the orbit of the Earth or on the Earth. And we are in the galaxy ourselves, so all the photons have to pass through the galaxy, including through the interstellar dust that the galaxy has. And this is something that we would like to clean, but also pretty much characterized very well. So interstellar dust is mainly made of graphite and silicate molecules. And it still has a couple of many interesting open questions left, including how ices can affect all of the optical properties of it, what's the exact size distributions of the grains, and the chemical composition. It's very important in star formation and planet formation, but it also couples to the magnetic field of the galaxy and to radiation in general. So it's very relevant for cosmological studies as well. In particular, it can emit thermal radiation, much like our human bodies do. This is why the military can see us through the buildings. And in the case of interstellar medium dust, it even though it can be very cold, around 1820 Kelvin, it will still be much brighter than a CMB, because the CMB basically reaches us at 2.7 Kelvin. So this can be a big problem, but also a very, very good data set for people who want to study dust, because if we look, for example, at the 857 gigahertz band in Planck, it's pretty much made of dust radiation. So many people have taken advantage of this aspect before to study the radiation, the properties of dust themselves. So one project I've done before has been to use the four highest frequency bands from Planck together with the 3000 gigahertz band from IRAS. And I've managed to map the temperature of the interstellar medium dust grains in 3 dimensions, which you can see in this map here. Here you're looking from the point of view of the sun in the galactic plane, pointing towards 180 degrees away from the center of the galaxy. So in this direction, with an angular separation of 90 degrees. So you're seeing basically this whole part of the galaxy. And colder regions are marked in red and hotter regions in blue. And we can see some very interesting aspects here, such as star formation regions, which are actually corresponding to the spots where we would expect to see both cold and hot dust at the same time. So this is a very interesting feature that we can actually see this at this resolution. And a very interesting thing for the future is that right now, this map has a resolution of 27 arc minutes. This represents the variation of the temperature. The density of the dust maps itself has more finer resolution of 5 or 10 arc minutes, depending on the degrading scale. However, upcoming CMB experiments such as CMBS4 and CCAT will provide data sets that will help us make maps that will be 5 times better resolution. In addition to the dust in the interstellar medium, there are dust grains present at many different scales in the galaxy. The closest one is to us is the solar system dust, also called ZODI. Then we have the interstellar medium dust, which the previous map was displaying. And we also have dust in other galaxies, the radiation from which forms the cosmic infrared background. And then we also have dust present in between galaxies, called the intergalactic dust. And in addition to dust emission, dust has other radiative processes as well, scattering and also absorption of light. And these last two usually are put together under the umbrella term of extinction. And they represent the amount of blockage that dust does to the photons that are passing through the dust clouds that are being encountered on the path. Usually, this extinction would have been so little in the regimes relevant for the CMB studies that it would have been ignored. However, these experiments have become so good nowadays that it is starting to become an important problem to follow. So to characterize this effect, the calculations are can be done in a simple fashion for grains that are large enough. We can consider that there's a radiation coming in that's going to be encountering a density of particles with a specific cross-section, and is going to basically be exponentially attenuated. So the difference made by the dust grain is going to have a dependence of 1 minus exponential to tau. Tau is considered to be the optical depth, which depends on the cross-section, the length of the dust cloud, and the density of the particles in it. Usually in the interstellar medium, we can make the approximation that we are in a thin optical depth regime where we can say that tau is much less than 1. So then the exponential can just approximate to 1 minus tau, which gives us a relatively simple relation between the intensity of the light that is in the dust grain and the absorbed quantity. In the CMB community, it is customary nowadays to parameterize the intensity of the emission coming from the dust grain with a modified black body function, where in addition to the black body radiation coming from the dust grain, there's a term of nu to the power of beta being added, a power law term that allows people to constrain the slope of the function. So to this, we can consider that the dust absorption of CMB can create a perturbation that's directly dependent on the temperature of the CMB, and it's just multiplying the optical depth and the modified blackbody part as well. So this formula holds both in intensity and in polarization. So these can sort of be introduced in analysis of experiments by not adding an extra parameter, but simply by subtracting the contribution that would be coming from the CMB term. So this is very important because it would mean that you would not have to degrade the sensitivity of your other parameters that you are modeling by adding another parameter in the fit. It would just be a decision of whether or not you're including this effect or not in the pipeline. The context of looking at the absorption of the CMB by the interstellar medium dust grains and by the CIB has been explored over decades, And there's works in the thread of academia that go back all the way to 1991 by Bond et al. And also Wright et al. Who have put models down for how to analyze this effect down to the quantum level of the dust grains themselves. There is a more recent work from 2017 that actually asks the question if there's something wrong with our physical models of the universe because we have not observed the CMB absorption of by dust. And article is basically saying, WMAC Planck and Firas have finished processing their data and they haven't indicated that they have observed this, but they should have observed this. So, what's going wrong either with our understanding of the extinction phenomena or with the measurements from these experiments. But I actually wanted to look into this question more, and I wanted to see would this effect have been actually large enough for these experiments to have observed it or not. So in the current work that's in preparation, I've calculated this effect again for both the interstellar medium and for the cosmic infrared background. And together with Doug Finkbeiner, we went back to look at the analysis that was done by him in 1999 and the Firas data modeling dust in the Milky Way to see if we can detect the effect of the dust absorption on the CMB. And unfortunately, it looked like the CMB absorption effect was lower than the noise of the fits. So we cannot tell anything about this by looking at the Firas data. And then I looked at what offsets would be for measuring beta at different temperatures on the sky using Planck. And the precision required for basically the shift in beta by this effect, by not including this effect, would be smaller than the precision by Planck. So basically, both all three Firas, WMAP, and Planck would not have enough sensitivity to detect this effect. So this clarifies why basically these experiments have not signaled this detection until now, and most likely there's nothing wrong yet about our modeling of this effect. New work by Nashimoto et al. In 2020 has shown that this effect is very, very relevant for polarization measurements of the CMB. Their calculations have compared this effect to the R value of 0.01, showing that even as this range is very important to include the CMB absorption by dust if one wants to hope to detect the signal. And for any R smaller than that, that would be required as well. And the same team followed up with more works on this, showing how this can be implemented into the pipelines of the experiments as well. In my own work in the past, I've looked at spectral distortions of the CMB. So Firas has measured the spectrum of the CMB, and up to its precision, it put a limit on the deviations from the black body radiation of the CMB that can be expected. But there are new missions in proposal, such as the PIXI mission, who is aiming to push down these limits 3 to 4 order of magnitudes, or even more depending on the design that gets funded in the long term. And I was looking at how would this CMB absorption by dust compare with the SED values of the distortions of the CMB. So in this previous work, I had run an analysis of what sort of offsets on the inference of the spectral distortion parameters would we get if we were to miss the CMB shadow caused by the cosmic infrared background or by the interstellar medium dust. So the results were that both in the case of the ISM dust and in the case of the CIB, the effect on the mu distortions would be very large. They would basically overshadow the shift in the mu distortion would make the distortion undetectable. For the Y distortions, the effect would be smaller in magnitude than the fiducial values. So that would actually be probably not so important. But given that these experiments are trying to target the mu distortion as well, it would basically be important for them to model the CMB shadow, both from the SM dust and from the CIB. So in summary, the CMB absorption has been treated in academic literature for many decades now, and it's seeing a new rise in popularity because we're approaching time where we have to take it into account for the experiments. It has not been observed yet because pretty much it was not within the sensitivity levels of the surveys that have been performed. And there are a couple of applications that are coming up that this would be very relevant for, which include the CMB polarization measurements and also spectral distortion measurements of the CMB. And it would be probably relevant for other applications as well as measurements are getting more and more precise. Thank you. And let me know if you have any questions and hope to see you at the discussion sessions.